Hello, I'm Nathan Sexton, and welcome to Lab 7. This is going to be about waves, and we're going to be doing experiment 1. So, start off going through our inventory real quick before we go through past any. Pretty easy. We got our handy dandy slinky, our spring scale. I didn't have masking tape, so I ended up having to use what I had, and stopwatch, which I'm using my phone for. My willing participant was my wife, but she's since walked off to clean our storage room, it looks like, and looks like she took my tape measure with her. So that's lovely. So going from there, let's kind of break down into this experiment. So it's all about modeling transverse and longitudinal waves to calculate the speed of a wave in this experiment. So I think the best way to start this out, got a little script over here, let me read this off. So a longitudinal wave is a wave that vibrates in the direction of propagation, where a transverse wave vibrates perpendicular to the direction of propagation. So we'll use those different waves to calculate the speed of the wave. So I have my area measured off. There should be able to see the tape right there to do the 2 meter, and the slinky is stretched out. Again, I don't have my willing participant anymore to. And then we'll have our motion from one side to another, again while holding my phone. That's kind of hard to go through doing any of that. I don't have a stand, but we'll get into everything a little bit later. No transverse waves. So going through, we have our spring scale right here, and this will actually help for when we go through our tables to give us the newtons, the Newton force, as well as the mass. So we go ahead and link that right there, just like that, and we'll get about 2 grams on our scale. Going through and that'll be our weight. And then we count the number of slinky loops. I originally got 49. I watched the instructor's, professor's video, went through, recounted a bunch of times, and I eventually went out to 50. And I got the distance marks, went through after we marked the 2 meter distance, sending one transverse wave along the course, and then waves different sizes, and then longitudinal waves. Use the distance mark stretched along the ground. And then we're going to use the stopwatch to measure the time it takes for one wave to return to you after it travels down the slinky. This is repeated 4 times after that. And then use the spring scale to measure the tension on the end of the slinky. Record this in value 2. And we're going to grab 20 coils near the end and pull them towards to increase the tension. And repeat this 4 through 6. Record these times and take. Alright, so now let's get into the lab workbook a little bit, because I think that's where we can really learn a lot more about waves. So, a couple good concepts to hit on. If a wave's, first off, the pre-lab question, if the wave travels through the air and is decreased by half, what happens to the wave in frequency? Well, it will remain the same, because the medium it's traveling through is the air, frequency is inversely proportional to wavelength. So when the inverse nature of the wavelength is half, the frequency is halved. So we got our math here kind of going through, getting everything. Let's get into the meat and potatoes of everything. Past Doppler effect, and here we are. This is kind of what I was describing. We got our kilograms and our loops going through. Looks like we have a mistake here. I'll fix that. Alright. So going down, then we have our wave time measurements for our different tables. And this is one of the best parts we'll get into to kind of describe everything. So the waves seem to, let's go. Alright, so the speed of the longitudinal waves compared to the transverse waves. So this is probably the most important thing. This is kind of what the lab's all about. The longitudinal waves appear to travel faster than the transverse waves. And for this is because they don't have as much resistance, because they travel a straight path versus the perpendicular path that the transverse wave has to do instead of the longitudinal. So this motion would make it so the wave seems to come out slower with the transverse. And then another good thing, I think we're gonna go into errors real quick, and we'll break down the different methods, right? So this is taken from our averages of our times, so our velocity from our stopwatch. And then past that, we're going to go through, and here's that for trial 1 and 2. And then past that, we'll go into a little bit of math, and we're going to have the Newton force, everything square rooted, the Newton force, the mass, over the number of loops, and our 0.2, which is going to come from our averages. Alright, then we'll go through all that, and we end up getting, let's see, 2.11 on the velocity, and then 2.00. Since there's more factors and more things that are measured, plus less chance for human error, the velocity from tension and mass density, I think is more accurate. But even so, the first one we got a 5.35% error and a 24.22% error on the second one. But still, they were relatively pretty close compared to a lot of the other experiments. Lastly, let's go instrument, as far as the accuracy of these instruments and the individuals reading them, human errors as far as stopwatch and everything. Also could have played a huge problem in this actual lab as we went through it. To wrap up, longitudinal waves travel faster because they have less distance to go and less resistance than the actual transverse waves, because they have to travel perpendicular, and that actually helps us go through that. When it comes to the speed of a wave, the less resistance they have to go through, the quicker it can move. So I'm going to wrap up here. Hope you have a great weekend, great day, and I look forward to the final exam next week.